Assalamu alaikum warahmatullah. Welcome to this third lecture, or actually the fourth lecture, but the third lecture of third week for our subject. And today we are not focusing on any new topic. Rather, I'm just trying to combine all of these things, and because if you move ahead too quickly, you will get confused because there are a lot of different methods, and most of the books cover different methods simultaneously in mechanical vibration books, so which end up confusing the students. So today I will just try to summarize different methods for you so that you know whenever you saw the name of those methods in a book or somewhere else, you don't get confused like it's something different. So this is the first thing we are going to do. Second thing is we are going to derive the equation of motion using all of those methods, and not for just linear method but also for the rotary method. And at the end we will see how we can the thing which we left off in last week, how the roots of the characteristic equation tells us about the behavior of the system. And that's the thing that we look to at the end of this lecture. So before going into detail, so lecture, call it 4, although speak 3 for that one. As we know that steps in mechanical vibration, there are 3 major steps. The first one is modeling the system. Second one is developing equation of motion. So from now on I will just call it EOM. So you should be able to understand that what EOM is. That's equation of motion. And the third step is solution of the EOM. Okay. So you might think like I'm hammering this again and again for the third lecture. My main purpose is just so that you are aware of all different methods that exist and how they can be applied. At least you should have slight this idea so that you don't get confused. We know that we have different kind of systems. We have first degree, second degree system with a damping, system without the damping. We have discussed all of these things in the last 2 lectures. So whatever the system you have, in terms of modeling system, you have 2 different approaches. The first one is called discrete modeling, which we have been doing so far, and the second one is lumped parameter modeling. I will let you know what it is. And the third one would be modeling for a continuous system. Continuous system, and I just don't get confused. What do you mean by continuous system? So discrete modeling, in which we, as I gave you the example of a car, we just represent the whole car as a single point mass. That's called the point mass. So what does it mean by the point mass? We are not dealing with the dimension of this. It is this thick, and this is the height, and so on and so forth. We are not concerned with that. We are assuming that whole mass of the body, which is car or aeroplane or train, is concentrated in this block, a dimensionless block. You may represent it as point. Let's call it M. You don't need to make a block. So that's called a discrete modeling, and then based on that you derive your equation of motion and everything, and you represent the whole system stiffness as one spring. You represent the whole system damping as a single or the series, or damper in series in parallel, so on and so forth. That's the discrete modeling which we have been doing so far. What is lump parameter modeling? So obviously in reality the systems are not discrete, they are continuous system. Means there's a car with a whole body with some length and breadth and height, and there's a the beam attached to a wall or present in any structure, and that beam is subjected to any load. That load may be impact load or the harmonic load or the ramp or the step loading. So obviously that beam has some amount of thickness and all of these things. So in the lump parameter modeling, we simplify this system, neglecting all of these height and width and breadth into the discrete system, into discrete model, by assuming the properties of this beam through solid mechanics. So we just import the properties of the beams through solid mechanics. We employ the theories of solid mechanics. Let's say the elasticity of the beam, the stiffness of the beam, and the mass and momentum and all of these things. We employ the theories of solid mechanics and employ directly into the discrete model system. So now whenever you are using stiffness value, you will be using actually the stiffness value present in solid mechanics of the beam. So that will be the value of K, maybe 4EI over L, something like this. So you have like this one. So that's a lumped parameter modeling. The third approach is modeling for continuous system. So we directly take the system with all of its dimensions, and then we consider the vibration of the system. So if it's a string, we also take into consideration the length of the string. If it's a beam or the bar, we also take into consideration the height and width and breadth of the bar as well. So that is a continuous modeling of a system, and we will look into the continuous modeling towards the end of the semester. Now, whatever the system is, the next important part is, once you have identified your system and once you have decided which approach you are going to take, you develop its free body diagram, and then based on that free body diagram, you develop the equation of motion. So now the equation of motion can be created, can be derived through different approaches, some of which we have already seen in the last lecture. I have told you, like, there's a Newton's law, Newton's second law, and it's derived from is the D'Alembert principle. I told you already. Just combine them together. D'Alembert method. That's simply concerned with F is equals to ma. Right? It takes into account all the forces, the spring force, damper force acting on the body, and it's causing some inertial force, right? And we have discussed what is the difference between these two in the last lecture. Another approach is, it's called Euler's method, and every method has its significance, some limitations. It is also known as Euler's Lagrange. I think he was a French physicist. Lagrange method. So what it does is, it is concerned with the change in momentum of the body. As we know, the rate of change in momentum is equal to the net force acting onto the body. So rate of change of momentum is equals to the net force acting onto the body. So, and we know the momentum itself is equals to mass into velocity. I will write it as x dot. Right? So just try to familiarize yourself with x dot, x double dot, and all of this, because we will be using this throughout the semester. So the Euler method models the equation of motion using the considering the change of momentum of a system. So that's the second part. Let's say we have already seen the derivation of equation of motion using the Newton's method and D'Alembert's method. Let's say the equation of motion we got from this one was mx double dot plus cx dot plus kx equals to 0. If we try to derive this using the Euler's method, so it will become d over dt, and since it was a mass spring damper system, so rate of change of momentum would be equal to mass into velocity equal to sum of all forces acting onto the system, right? And which will be equals to minus cx dot for the damp one and minus kx for the spring one, and you just take it on the other side. So, and you know that's already x dot, so double derivative or another derivative of x dot will be x double dot, so it will become mx double dot plus cx dot plus kx equal to 0. So you will again reach the same equation of motion, although you are using a different approaches, and I will give an example through our rotational system as well, so don't worry about this one. So why do we prefer Euler method in what some cases, especially for the rotational system? It is difficult to apply this one Newton's law, because you have to deal with fx, fy. If like pendulum is moving here in to and from motion, so you have, let's say pendulum is here, you have to deal with fx, fy, and so on and so forth. So Euler method, uh, like it's too short in such scenarios, it will quickly give you the equation of motion. Especially when you're dealing with the fluid dynamics, the flowing system, so it helps you to quickly derive the equation of motion. Another method for deriving the same equation of motion is based on energy. That's called the energy method. So what energy method says that the total energy of a system is conserved, and we know that the energy cannot be created nor be destroyed, so we assume that there is no loss of energy in the system. And it is, as you know, by this logic, it means the system deals with the undamped system, so there is no damping involved, because damping itself is a loss of energy. So it tells like uh, rate of change of kinetic energy plus potential energy, which is actually the total energy of a system, is equal to 0, where kinetic energy, T is kinetic energy, and obviously we discussed in the last lecture, which corresponds to mass of a system, is equals to half mx square, mx dot square, and for the potential energy is equals to, it corresponds to the spring or the stiffness of a system that is responsible for storing the potential energy, that is equal to half kx square, sorry, not dot, kx square. So you can now substitute these values here. It will be d over dt half mx dot square plus half kx square equals to 0, so it becomes, obviously this 2 can be cancelled out from 0, it becomes, and d over dt of x dot, it will be mx double dot for this one plus half, oh sorry, not this one, just erase this one, it will become mx dot into x double dot plus kx into x dot equal to 0, and it becomes you can just take out the x double dot from here, it becomes mx double dot plus kx equal to 0, because the system is without the damping, right? That's simply a derivative of x dot square, so 2 comes down, it cancels out 2 from here, the second power comes down and it cancels out this 2, and then we can simplify this one. This is how you can use the energy method to drive the similar equation of motion. So all of these methods that I'm quoting are just to derive the equation of motion from the model. They are not the solution method. So where do we prefer this energy based method? Whenever we're dealing with a conserved system where the energy is conserved mostly, and yeah, so although it's not very it can't deal with much complex systems, the pure energy method, but it is really helpful. If we are dealing with a simple system, it will quickly help us to derive the equation of motion. Another method is the Lagrange method. It is one of the most powerful method and widely used, especially in the multi-degree of freedom MDOF system. It's called Lagrangian approach or Lagrangian method. So what the Lagrangian method says, it says the Lagrangian coefficient L is equals to the difference between total kinetic energy and the total potential energy. And the generic form of equation of motion for the Lagrangian method is d over dt equals to differential of Lagrangian method or Lagrangian coefficient with respect to the x dot and minus partial derivative of Lagrangian coefficient with respect to x plus partial derivative of damping with respect to the x prime. That's a general equation of motion, general characteristic equation of the Lagrangian method, and this will help you to identify the equation of motion. And here D is kind of Rayleigh dissipation, which is equals to half Cx dot square. How we can identify this one? So we know that T equals to half mx dot square. We know V equals to half kx square, and we know D that this is D. So if you substitute this value into this one, equation 1, you can say it becomes T minus V, it will become half mx dot square minus half kx square. And now if you try to find out this one, the partial derivative with respect to x for this one, it will become, it will reduce to minus k of x, because if you try to differentiate with respect to x only, but this is velocity, that's not resistance, so this acts like a constant value, it becomes 0. We are only left with this one, so the power comes down, 2 will cancel out, and we are left with kx. This is simply a differential equation solution. And we know that if you try to differentiate with respect to the velocity, now this will goes to 0, this component, and we are left with mx dot. And now for the generic equation of Lagrange, we have to differentiate this component with respect to time as well. So we can differentiate with respect to time. So d over dt of partial L over partial x dot, it become mx double dot. Now you can substitute all of this into your generic equation of motion here. This equation 2 for the Lagrange method, it becomes mx double dot minus of partial L by partial x, that is minus of kx, so minus of minus kx, and then the third one is partial d over partial x, so plus the value of d, that is half cx dot square. That is the differential of the damping one, so it also becomes cx dot only. So because we will take the differential with respect to x, it will become cx dot, and that's all equal to 0. Or you can rearrange this one, mx double dot plus cx dot plus kx equal to 0. So again you reach the same equation of motion for the 1 degree of freedom spring mass damper system using the Lagrangian method. So it is very easy for the multi-degree of freedom where you have a lot of independent coordinates, and for that reason it is primarily used in robotics and some biomechanics, also used for finite element analysis. so it's much easier to use in such scenarios compared to the common Newton's method. Now another method to approach the same equation of motion, that's the virtual work method. So again, just recall, we are just looking at the methods to drive the equation of motion. So if you just draw this one, and that's a virtual work method. So virtual work method. So what it tells, this method uses work done by the force through the virtual displacement. So what does it mean by for a vibrating system? So the total work done will be equal to the work done because of inertia plus work done because of spring plus work done because of damper. So it assumes that all of the elements of vibrating system, that is damper, mass, spring, all of them are doing some work, and because of that there's some distance being covered by the system, and the work is set to be done. So since that system as a whole is in equilibrium, so it means the work of damper is cancelling out spring, the work of spring is cancelled out inertia. So because of the net work is zero, so all of them, the system is in equilibrium, right? So what is the actually values of this virtual work? So for inertia, this virtual work because of mass will be equals to, we know the work is equals to force into distance, and because we know the force because of mass equals to ma, so it will be mx double dot f into d. The work is equals to force into displacement. So the work done by the inertia would be equal to force, that is f, inertial force, into d, that is the distance covered, net displacement. Same is the case for the spring, what you call spring virtual work. That's wk, and we know the spring force equals to kx and into the displacement. And for damper, work done because of the damper, that's equals to cx dot into the displacement. Now you can substitute all of this into the equation of motion, so it becomes mx double dot into displacement plus spring force kx into the displacement plus cx dot into the displacement equal to 0. And since displacement is common, just take out a common and take it on the other side. So mx double dot plus cx dot plus kx into displacement equal to 0. And since displacement cannot be equal to 0 because there's something happening with the system, so for sure the net equation of motion will be equal to 0, and for that we need to solve it and find the solution. So again we reach the same equation of motion using the virtual work method. So these are all of these methods that we can use to drive the same equation of motion, depends upon what we are dealing with. Obviously when you're dealing with a multi-degree of freedom system, you can't use the Newton's law. It's too difficult for apply to all of them. In some cases you can't do it. So you can use the Lagrange approach, you can use the virtual work method. So again, this virtual work method is good for multi-degree of freedom, especially for being structures. It can be used in finite element analysis. So that's the different approaches to drive the equation of motion. But and all of these methods will take you to the same equation of motion. Now what's next? The next is, once you have found applied all of these methods to drive this equation of motion, the next thing is to solve that equation of motion. Again, for solution you have different approaches as well based on your needs, what you want to find out from that system. One of the solution method we discussed in the last lecture, which was generic differential equation based system. So for the solution one, we again have different methods for the solution of the equation of motion. If we just switch towards the next page. So the first one, that is the standard classical method of characteristic equation. Characteristic equation method, where again if we have the equation of motion and then we use the solution of the equation x of t equals to c e lambda t, and then we take the x dot of t, then we find x double dot of t, and then we substitute x dot and x double dot and x into this equation a, and then we find the characteristic equation. We did all of those steps in the last lecture, and we find m lambda square plus c lambda plus k equals to 0, and once we have this quadratic equation, we try to find the roots of this quadratic equation using minus c plus minus under root c square minus 4mk divided by 2m, and just or if you just don't use this one, the next thing we did was we linearized this equation and we found the natural frequency and the damping coefficient. So there are both ways. You can just directly use this m, c and k, and if you remember in the last lecture what we did, we linearized this our equation. We divide the whole equation by mass, and then we got x double dot plus d by mx dot plus k by mx, and we said that k by m is equal to omega square, and omega is simply the natural frequency, and d by m is simply twice of damping coefficient. So these are just parameters that have some physical significance or tells about some physical interpretation of the system. You can do without linearizing the equation. Linearizing is this step of dividing whole equation by m, and you can do with the linearizing equation as well. In both cases it depends upon either you are interested in finding the natural frequencies or you're just interested in finding the time based solution. So it's up to you. So that is the one of the method, equation of motion, the characteristic equation method. I'm not going to dig deep into this one. We will see it soon in detail. The second method, which is the same method actually, that's the extension of this one, you can say. It has, if it is not equal to 0, rather you have equation of motion as mx double dot plus cx dot plus kx. It's a force vibration, so there's a force involved, f naught sine omega t. Let's say on your system you are applying some f naught sine omega t of harmonic force. So you have to, instead of finding the solution directly, you have to find a complete solution of homogeneous plus particular solution. So there's a separate way to so this particular solution corresponds to the solution of because of this force, the solution because of the movement by this force, while this one is simply the same solution. So you add the solution of this one plus you find another solution and you add them together to find the total solution of this such system which is under the force vibration. Another approach, if you have the multi-degree of freedom, I'm just erasing this one at the moment. If you have multi-degree of freedom, that's called the state space method. It's not only the modeling it's not only the equation of motion method, rather it also solves that one. So in that one we find the matrix x not equal to ax is equal to ax, and then A is simply the matrix that involves the natural frequency and the damping of our system. I'm writing this for the same mx double dot plus cx dot plus kx. Don't get confused with what all of these things are. We will discuss this in detail in future. I'm just trying to let you know all of these different methods, so that whenever you encounter this in your book or in your notes, you don't get confused. They are just different ways to do the same work. So we are doing the same work using different methods. Some methods are strong in one aspect while they are weak in other. Some methods are weak in other aspects while strong in the other one. So that's for the multi-degree of freedom, especially important for MDOF system, multi-degree of freedom system. Right. Another method is that we are going to use widely in our course. I'm not going to stick much with this one. It's too lengthy, hefty. It's good, you should know it, but it's not very good method, what I feel. So there's another method that's called the Laplace transform solution. Laplace transform solution, or Laplace transformation based solution. So what it does, once we have found our equation of motion, it performs a Laplace transformation of that equation of motion. Mx double dot plus cx dot plus kx equal to 0, and then you will convert that. What the Laplace transformation does, it transforms differential equation into algebraic equation. So now when it is an algebraic equation, it is easy to solve. You can use the same quadratic formula, you can use method for polynomial equations. So this is what Laplace transformation does. It converts the differential equation to algebraic form, and then it makes it easy for you to solve. And there's some other application for this one as well. So it will convert this into, it will become a bit longer like this. So if it is double derivative, it will become s square. I will do a separate lecture of what the Laplace transformation is, so that you will revise it, although it must be covered in your mathematics course. Minus of s x of 0 minus x dot of 0, and that's all, plus c, it becomes s x of s minus x of 0, that's all, and plus x of s equal to 0. And here you have x of s as your independent coordinate, and then you can write down your equation in the form of the small x is not very good, I'm just making it smaller. Whole divided by our m square plus cs plus k, where s is the Laplace variable, and it can be further transformed into the I omega, but yeah, please stick here. So it is why do we use a Laplace transformation? Again, first reason is it converts a differential equation to algebraic form, which makes it easy for solution. It gives a total solution, both transient and the steady state, while in the time domain we have to solve it separately. We can directly solve from the Laplace transformation with a less number of steps. It's really easy to apply, and there's a thing in the Laplace transformation called transfer function. Transfer function is actually equal to output over input of whatever the system you're dealing with. So it briefly and quickly tells you what will happen if you give this input to your system, what will happen to your system. So it's really good when you're dealing with a frequency domain and when you're dealing with a transient system as well. So this is how we can do it. So now there are some other methods as well. Energy method, energy conservation approach. There are some numerical integration. Obviously we are not going to discuss all the methods in our course, we can't do it because we have to do all the course from all different types of methods, but we obviously will try to cover all of try to cover somehow all of them lightly, not too much. Another one is like modal analysis. We will cover this one, that's an important one. So that's all for the different types of things. Now there are some other methods as well which are mostly used for performing the FEA, finite element analysis of our dynamic system. Then we can pursue some, but what we are going to focus on in this course would be this characteristic equation in the beginning, and then we will jump to the Laplace transformation because it gives a really quick solutions, and we will do the remaining mechanical vibration using the Laplace transformation, and we will touch the modal analysis as well towards the end of this course. That was the quick summary of the whole mechanical vibration, so that whenever you read any book yourself you don't get confused what's happening. So because you will see sometimes they're using this method, sometimes they're using other method, but don't get confused. They are the different methods for performing the same job with some advantages and disadvantages in this case. So next is we are going to look into some rotary systems. So we'll drive the equation of motion of the rotary system using both the Newton's law method and using the Euler's momentum method. Again, just keep in mind we are still working on equation of motion, we are not into the solutions of those systems. So I want you to get familiar with equation of motion first, then we will jump towards the solution one. So we are going to drive the equation of motion using the Newton's law and using the Lagrange Euler's method for the rotary system like a pendulum or any wheel, flywheel. So let's jump towards that. So now let's assume we have a rotary system. So let's jump to the new page. Now lecture 4, lecture 4. Let's assume we have a rotary system like this. And there's a pendulum moving, and let's call it X, let's call it Y, and pendulum has some mass obviously, and the length of the string that is attached to the pendulum is L. Now we have to find the equation of motion for this one. So the first method we are going to employ is Newton's method, and obviously Newton's method is equals to summation of all force equals to 0, which is, if you go to the D'Alembert's method, it's equal to 0. If you go to the Newton's method, it's equals to MA, because in D'Alembert method it takes the MA, include the inertial force into the summation of all forces. So just stick to this one, and since it is vibrating in along two axes, so obviously we have to take into account the x-axis and y-axis as well. So summation of all forces along x-axis should be equal to 0, summation of all forces along the y-axis should be equal to 0. Then our system will be in the equilibrium. So what are the forces acting along x-axis? So this is x-axis, so there will be tension in the string that is acting opposite in direction, that's a tension. So there will be a x-axis of the tension and there will be a y-axis of the tension. the component of the tension along the y-axis and the component of tension along the x-axis. So if this is theta angle, let's say at any point theta, that becomes t sine theta, and that becomes t cosine theta, and there's a mass of the pendulum acting vertically downward, that's mg. So now we can write the equation of motion for the x-axis. That becomes, let's assume that all the motion towards on the right side is positive and everything towards the top is positive, right? So you have to define a convention at the beginning so that you don't end up mixing up all of these. So fx equal to 0, so t sine theta is towards the negative side, so minus t sine theta equals to mx double dot. That's our equation 1, because t sine theta is balanced by the inertial of this mass along the x direction. And then we have the summation of all forces along y-axis. So we have along y-axis the force acting vertically down, the force because of weight acting vertically downward, that's minus mg. Then the tension acting vertically upwards, that's plus t cosine theta, that's both equals to my double dot. So that we have two equation of motion now. But if you just see here, we have four unknowns here, and we have two equations. What are the unknowns? We don't know the theta, we don't know x double dot, we don't know y double dot, we don't know tension. So it means you should have equal number of equations. You should have equal number of equations and the unknowns so that you can solve them. But here we have four unknowns and we have two equations. So the rest of two equations we can find using the kinematics. So from kinematics we can see, if we check out our string with the mass pendulum at the end, and this is the length. So the x distance covered by the string is equals to L sine theta, and the y distance covered by the string, if this is a string, that's equals to minus L cosine theta. So from here, because we don't know the x double dot and y double dot, so from here x dot will be equals to theta dot L cosine theta, and y dot would be equals to minus theta dot equals to into the L sine theta. And if you find the x double dot, and you know that you have the general method to solve the differential equation for the multiplication. So you have d over dt of u into v, it becomes u into dv over dt plus v into du over dt. This is how you solve if there is a multiplication involved. Just write it properly, of u and v. So we are going to use the same thing, that's u and that is v. So that is v and that is u. So you can apply the same method here. So it becomes minus of theta dot square sine theta of L plus theta double dot cosine theta, L cosine theta, better to write L here, L sine theta, theta into L cosine theta. And same the case for the y, double derivative of y, it becomes minus theta dot square L cosine theta and minus theta double dot L sine theta. So now we have two more equations. So we have two more equations, like equation number 3, equation number 4, and the next thing is we have to substitute this equation into the our other equations. Just write it down again. I'm writing down all of them together so that we don't end up confusing this one. So equation 1 was mx double dot equals to t sine theta. That was equation 1. Equation 2 was my double dot equals to t cosine theta minus mg, and our third equation is x double dot equals to minus theta dot square into L sine theta plus theta double dot L cosine theta, and fourth equation is theta double dot L sine theta plus theta dot square L cosine theta. So that's equation 3 and that's equation 4. So the next thing is we can simplify, because we can simplify it to remove the unknowns as much as possible, because we are only concerned with the dynamics or the motion of the pendulum, which is based on theta. So just try to eliminate all other unknowns and write the equation of motion in terms of theta. That is easy to determine because we can't find out x and y all the time. So let's multiply equation 1 by cosine theta, and for equation 2 multiply by sine theta. So it will become, the new equation 1 will become m mx double dot cosine theta is equals to minus t sine theta cosine theta. That was minus here. And for equation 2 it will become my double dot sine theta equals to t sine theta cosine theta minus mg sine theta. Right, now we can simply add them together, add both of these equations together, so it will cancel out. We are only left with mx double dot cosine theta plus my double dot sine theta, and you take this on the other side, plus mg sine theta equal to 0, and here you can substitute the values of x double dot and y double dot so that you end up eliminating the x and y altogether, and just take m on the other side. So you can take m x double dot cosine theta plus y double dot sine theta plus g sine theta equals to 0. So m cannot be equal to 0, so it necessarily means this equation will be equal to 0, and we can substitute the value of x double dot and y double dot from our equation 3 and 4. So that this makes, you can simplify yourself, it will convert our equation to theta double dot L cos theta minus theta dot square L sine theta into cosine theta plus theta double dot L sine theta plus theta dot square L cosine theta plus g sine theta equal to 0, and you can simplify all of that together. So if you want to add cos into cos square theta, and the sine square theta is equals to 1, you can just simplify all of them together. You will be left with L theta double dot plus g sine theta equals to 0. That is your equation of motion, and that is second order homogeneous. That's second order because you have double derivative involved. Homogeneous because you don't have anything on the other side, there's no external force involved. Non-linear ODE. Right, oh sorry, that's not the linear ODE, ordinary differential equation. That's second order homogeneous ordinary differential equation. So you see, if you employ the Newton's law, it uh, it made it too complex to drive the equation of motion. You have to employ the kinetics for that one and all of this together. Now just try driving the equation of motion for the same system using the Euler's method. So I will just copy, sorry, I'll just copy this one here. Now I'll try to drive the same system using the Euler's method. So what the Euler method is, it says the net summation of all the moments acting on the body is equal to 0. That's a body in equilibrium, which is equal to the net force acting onto the body. So the Euler's method suggests that summation of all force moments acting onto the body is equal to the net force onto the body, and since it is a rotational motion, it will be equals to I alpha, rotational motion, where I represents inertia, and instead of x double dot we have alpha, which is acceleration, angular acceleration. You can write it as x, you can also write it as theta double dot. So just leave it for now. Now I'm erasing this part as well. We are not concerned with this one in this method. Okay, so again let's assume the anti-clockwise movement is positive, and this is, that's theta here, and so for that becomes L sine theta, and this becomes L cosine theta. That's a point mass, and we have defined the convention that anti-clockwise is positive, anti-clockwise movement is positive. Now what are the movements that are acting onto the body? So the movement that are acting on, the only force that is causing movement is the mass of the pendulum itself, and which is causing the clockwise movement, right? So summation of all movements equals to I alpha, and here the force and the moment here is equals to, this is force, that's minus is because of the direction, mg force into the force arm, that is L sine theta, equals to I alpha, right? Now the next thing is that's the, here the inertia is the inertia of the point mass, right? But that is equals to the inertia about the centroid, the center of mass, plus ml square. That is the distance between the center of mass and the point about which the body rotates. So this body, that is the pendulum, is rotating about this point, right? So the moment of the inertia of this pendulum is equal to the inertia about its center of mass, inertia at this area somewhere, at this point somewhere, and inertia plus ml square, where L is the distance between this center of mass and this point about which the body is rotating, right? So since this body is not rotating around its own axis, so this becomes 0. The body is only moving in the circular path, but it's not rotating about its own axis, so this becomes 0. So the total moment of inertia of this point mass is equals to ml square. Is it clear? So it becomes ml square alpha plus mg L sine theta equals to 0. So we can write the alpha as ml square theta double dot plus mg L sine theta equals to 0. So we can take m and L as common. It becomes L theta double dot plus g sine theta equals to 0. And since ml cannot be equal to 0, mass into the distance, because m has value, so that's a trivial solution for us. So necessarily L theta double dot plus g sine theta equals to 0. Now we have the same equation of motion we derive using the Newton's law, but you see it has greatly reduced our work. We were able to find this equation of motion in merely like 4 steps. So now you can see, now whenever you encounter such systems, rotary systems, so now you can decide, okay, I have to go towards the Euler's method instead of using the Newton's method. Although you can use the Newton method, but it will greatly increase your task, it will increase the complexity. So and you can use the Euler method. So now you will be able to identify that all of these methods are correct. All of these methods are for the same job, but it depends upon your situation, what kind of system you are analyzing, what is the dimension of the system, what are the scenarios or the condition of the system. So based on that you can choose appropriate method for drawing equation of motion and for finding the solution. So that was just to show you how you can use the different methods to solve the same problem. And that's all for this lecture. In the next lecture I will be uploading, we will discuss the thing we left off. Sorry, in the lecture number 3 I think we left this method here. So we are going to discuss how the roots value, how the roots tells us about the behavior of the system. So it's just like a small topic we will discuss briefly, and then we will jump towards the Laplace method. That is another method to solve the solution, to solve the equation of motion. So now we will be moving towards the solution of the equation of motions, and I will be uploading an assignment where you will have to derive equations of motions only. You don't have to solve it, just derive equation of motion and just decide yourself which method you should be using. Either it's a Newton method, or it's a Euler method, or it's an energy method. We are not going to discuss all of them, but for now we are going to stick to these 3 methods for equation of motion. And should you have any question, you can drop me a message on WhatsApp or email. And again, apologize if I reply late, because I'm into a lot of things these days. So again, I sincerely apologize, but I will make sure that I answer to all of your queries, and I hope so all of you are safe. I mean, see you next week inshallah. Assalamu alaikum.